All right. Hopefully this is recording, and if it's a failure and my recording fails, I will just do the lesson myself over the weekend, all alone, and record that. Okay, ladies and gentlemen, welcome to extra session number 1 for those who are about to crush the AP exam in the spring. So I've already sent this link out, but I will continue to remind and send links. I'm generally going to link to this document, everything, and try to avoid using um, the canvas as possible, just so there's not cross-contamination confusion. And probably I'll just use Canvas for like if I give you quizzes or tests to try, just for your own benefit. So um, no problem. But that's the long and short of it. So today I want to talk about or introduce you to the concept of kinetics and what do we do with it. And it is kind of interesting that we're starting today because we just started equilibrium as well. And really, kinetics informs equilibrium. I mean, the whole basis of equilibrium is that we have two opposing processes coming to a constant or an equal rate. So to talk about what affects the rates of reactions is obviously behind that. And that's really what the first chunk of today's lesson is. And I bet you could probably figure most of this out on your own after I start with one really simple introduction. So the basis of what we call kinetics, which is basically the measurement, so this is going to be under unit 8, even though we're in 9. What kinetics tries to figure out is what affects how fast reactions go. So that really, if you think about it, is interesting because when you think about kinetics, you're talking about reaction rates. When you talk about equilibrium, you're talking about where does the reaction end. So we're talking about here, how fast does it go? What influences that versus where does it stop? So let's start with those kind of main points of what influences the rate of a reaction. And I think I'm willing to bet that you could probably already take a stab at answering this. So what I'm going to ask you is, if you considered the concentration of the reactants in a reaction, how do you think this would influence how fast the reaction goes? Just let's guess a bit, and then I'll give you a theory that see if it's consistent. Any thoughts? So I'll start. If you have a higher concentrations, what do you think will happen to how fast the reaction goes?
Faster.
Yeah, that makes sense, doesn't it? The more stuff you put in, the faster it will go. I mean, it seems to be logical. Maybe we don't know why yet, but it makes sense. What about the surface area? Do we even know what that means? Like, I'll give you an example. You take a sugar cube, you put it in your coffee. You take sugar, powdered sugar, you put it in your coffee. Which one do you think dissolves faster?
Powdered sugar.
Okay, so which has the higher surface area?
Powdered sugar.
Yeah. So it seems to make sense that the more pieces we cut up the reactants into, the more areas of contact they have to react at. And that seems like it makes sense that that should be able to react faster. What about temperature? What would your gut tell you if you raise the temperature of a system? What do you think will happen to the rate of the reaction?
It goes faster.
Again, it seems to make sense because we add more energy to the system and things are more energetic. They tend to be able to break their original bonds and do something different, right? So this is just gut instinct we're going on right now. I haven't even told you anything yet, and you're basically guessing everything correctly. Do you all know what a catalyst is back from biology or first year chem?
It's a substance that makes a reaction go faster.
Yeah. So by definition, its mere presence makes a reaction faster. Sorry, this is glitching on me. And we'll get into how they work a little bit in detail. But for now, just the idea that there's a catalyst present, we know that that's going to speed up a reaction. And another kind of corollary to that, we should add the fact that catalysts don't get consumed or used up. A catalyst is a material that helps the reaction but doesn't directly get used like a reactant. Okay, and then the nature of the reactants is really talking about the difference between, let's say, like a reaction like precipitation versus, let's say, a reaction like rusting. I think we'd all agree that precipitation is really fast. Like as soon as you mix the chemicals, you see it form. And that rusting is really slow. I think we'd agree to that. And what that gets down to in large part is the nature of the reactants themselves. In the case of precipitation, you have ionic compounds already separated into free ions in solution. So as soon as they meet other ions, they can almost instantaneously find them and form these little tiny pieces of solid that we call the precipitate. But rusting requires something tough and solid like iron over time interacting with water and oxygen and other things in the, like elements like, let's say, sodium chloride or other things in the water that very slowly over time eat away and react with the metal. And so the nature of the reactants themselves can also be a factor. So let's look at maybe how do we account for these differences? What's the underlying theory we're going to use to understand this? So I'm going to go with the concept of collision theory. This is a pretty simple model that will help us visualize and understand everything we just said. So here's the essence of what controls the rates of reactions. Number one, three things have to happen for the reaction to happen at all. First, the reactant molecules must collide. If they don't collide, they can't react. Two, that collision has to have a minimum energy that we're going to later define as the activation energy. Why does it need a minimum energy? Well, in order to make something new, we have to break what's already there.
Why are you?
Oh, I'm going to mute you. Sorry. But, just because things hit doesn't mean they break. You ever drop a glass on the floor and go, and then it just bounced and didn't shatter? And you're like, whew. Well, point one was met, but point two wasn't. It wasn't a big enough fall with enough energy to break the glass. And so in that sense, we have to not only collide, we have to collide with a sufficient amount of energy. And point number three, they have to collide the right way, in the right orientation, with the right aim. So again, we can analogize this to something like throwing free throws on a basketball court. If you only shoot, if you never shoot the ball, you're never going to make one, so that would not reach point one. The ball has to get to the basket, first of all. Number two, it has to have enough energy to reach the basket, so if you throw free throws all day, but you don't throw them hard enough, you're never going to score. And of course, even if you throw them hard enough, if you don't shoot them in the right direction and the right aim, you're going to miss. So when you put all those pieces together, what you get is how the things we just talked about make sense. Because point number one has to do with collision frequency, right? If you look at concentration, the reason why a higher concentration makes the reaction faster is because you're increasing the rate of collisions. That's the key point. And so let's kind of add this layer of why. The more chances you take, the more chances there are for the reaction to happen. So I like to use dating as an analogy in this situation. So pardon if this, so let's say, you're in high school right now. Except we're not in classes, so this analogy starts to fail. But imagine we're all in the building. There's about 2,000 of your peers, people in your age group who you could potentially date. And, that's a pretty high concentration. And so there's a lot of people that you could potentially date. There's a lot of possible collisions. And when you go to college, again, the same thing. When you go into the general world, now you're diluted into a world where you work, where there's people of all kinds of ages, and now there's fewer and fewer people probably that you can accessibly date, and therefore the collision frequency goes down. It gets a lot harder. So my personal story, when I was in high school, I was just one girl, sophomore year. I fell in love. I was totally in love, right? So I sat there and I plotted and I planned and I tried to really focus on just on this one person, to just, never really approached her. I was too nervous and all that stuff. And for like 2 years, I held a torch for this person. And I always thought, okay, one of these days I'm going to actually ask her out. I just got to be perfect, otherwise it's going to fail. And I just sat there. And of course, I went through 2 years with like no dates. So sad, right? My personal story. Now, here's what I learned after I took chemistry.
Sorry, I forgot that there was a
That's okay.
thing.
Well, here's
But I
what.
also have a thing at 2:30, so.
No worries. So what I learned from that experience once I took chemistry is that if I want to have more dates, I have to take more chances, right? I have to increase the concentration and the number of collisions. So now I changed my attitude. Like, you want to go out with me? No, okay, never mind. You want to go out with me? No, never. And it just kept going down the line. Eventually, law of averages, someone's going to say yes, right? So the point I'm trying to make is the more chances you take, the more love you make. And I mean that, of course, in a perfectly innocent way. But my point is the frequency of the collisions increases the rate of the reaction because there's more chances. The surface area does the same thing, right, in a different way. Surface area matters when we have a heterogeneous reaction, like solids reacting with gases or liquids. But again, it's based on increase. Oh my gosh, this writing thing is failing here miserably.
I didn't miss
Increased.
anything too important, did I?
No, just my introduction. I'm recording this, so.
Okay.
But it's really the same thing. It's increased collision frequency. And let me show you a better image. Sorry, my gosh, this is really not writing well on this. But take a look at this image down here. If you take a solid object, like let's say a piece of wood, and you want it to burn, it takes forever because the oxygen that has to react with can only access the material at the surface. All the stuff interior is not going to burn because they can't get oxygen. But if you grind it up into smaller sticks, now there's a lot more points of contact where the oxygen can react with it. And so by increasing the surface area, you've effectively increased the collision frequency, and therefore there's more chances and the rate will go up. Anyone who ever did a campfire knows this, because you know that you start with kindling, which is like, bird nest or whatever, dry grass, and then you put small sticks, then you put the big logs. Otherwise, it's really hard to light a fire. The temperature effect, on the other hand, really combines both. So what it really does is it increases the frequency. Oh my gosh, this is such a fail on this. Why is this failing so bad? Anyway, I'm just going to transition to a sheet here. So I was doing temperature. This one increases the frequency and force of the collisions. Meaning, because the molecules are moving faster, right? Remember, temperature relates to molecular speed. What we're saying is, when we raise the temperature, molecules are moving around faster and faster, and they're also colliding with objects harder and harder. And so what that really translates to, if we look at another image here, if you remember these Maxwell-Boltzmann distributions and how they change with temperature, let's imagine that this dotted line on this graph represents that minimum energy of the collision that's needed for the reaction to occur, for the collision to actually produce the products. Well, temperature 1 is the colder temperature, and you'll notice that only a small fraction of the molecules are going to have enough energy for the reaction. But when you raise the temperature, it shifts that curve, and now a much larger fraction of molecules has the minimum energy. So as you raise the temperature, you're not only making more collisions happen, but even more importantly, more of those collisions will be effective in producing a change. And so that's how the temperature effect works. And sorry, I couldn't write it here, but it's like my pen thing was really starting to be a mess. How does the catalyst affect the reaction? Why does a catalyst speed up a reaction? Well, again, we do more of this later, but there's really two different ways it can work. One, it can lower the activation energy, making it easier. Meaning that it provides a new collision pathway, like a new sequence of collisions that makes it easier to happen. Or two, it can improve the aim of the reaction, meaning it can hold molecules in a specific orientation and as a result make them more susceptible to attack. That's what mostly the enzymes in your body do. They have very specific shapes so they can fit certain molecules in. You probably remember from bio like the key and lock model where it's, oh, this goes here, this goes, whatever. We talk more about it later. But I just want to show you there's two different ways that a catalyst work. So it really just makes the reaction more efficient in more than one possible way. And as a result, makes the reaction go faster. So this is the essence of what factors affect the rates of reactions. To review, higher concentration means more molecules are hitting each other in a given time, and therefore we expect more possible collisions, and therefore faster reaction. Higher surface area we saw does about the same thing, because when you have a solid interacting with a gas or a liquid, it can only interact with the surface. And so increasing the surface area means that you get higher collision frequency.
I have a question.
Yes, sir.
So, but what if you increase the temperature of a solid? The molecules can't really move around that much.
That's true, but you do, because of their increased vibrational motions, in a sense have weakened the attractions holding them together. And again, since reactions really depend on breaking the original bonds to form the new bonds, anything you do that weakens the original bonds, we would expect to tend to increase the rate of the reaction.
So what you're saying is that if you had like something like by heating up wax, like let's say you put a thing of wax, like a candle in like an oven and heat it up to 300 degrees Fahrenheit, not hot enough to melt it, and then you set the candle down, and then you lit it with a flame. You're saying it would light faster and burn faster.
I'm saying in one sense, yes, but that's a very complex system, although
Okay,
it doesn't
I
seem like.
understand.
But yes,
I was trying to simplify it as much as possible, but I don't think I did a very good job.
I think it's fine. So what we're going to do now is look at how do we express the rate of reaction? Like how do we even measure it? And this is the one chapter that's almost more physics than chemistry. Like a lot of what we do here is rates. And if you took physics, it's completely analogous. And if you took calculus, we can apply calculus to this. We don't have to and we won't, except for people who want to see it. But I'm just saying the idea of measuring a reaction rate is really simple on the average. So on average, if we measure some property of a system, mass, volume, temperature, conductivity, concentration, pressure, color, any of these properties that can change over time, the rate of the reaction can be tied to any of that. So as long as there's some measurable property and we can watch it happening over time, we can get a rate, right? This is literally just the rate formula from when you were in grade school. Rate times time equals distance, right? It's the same idea. So usually it's most likely, as the definition says here, we're going to do it in terms of the reactants. Most of the time we're going to monitor reactant concentrations and watch them disappear. Sometimes that's hard to do. It's easier to monitor a product, so we might watch how fast the product appears. But in either case, there's a way to relate those, and that's what we're going to show. So, as I said, there's a lot of different properties that we can look at. And one of the demonstrations I would have done is literally what Will just talked about. I would have put a candle on a electronic balance, and then every minute we'd measure how much the weight has changed. And then we would have shown over each interval of time, okay, well, how fast is the candle burning? I mean, it's not that hard of a concept in that sense. But it does get a little bit more complicated when we want to actually define it. So what I'm going to do is I'm going to kind of work from a graph and talk about some stuff about this graph, okay? Because what we really need to determine is when we talk about rates, what's the difference between talking about how fast it goes on average versus the instantaneous momentary rate? And how do we tell the difference? So I'm going to start with this graph, and most of the rest of this lesson is going to be based on this graph. And then I'll show you a couple examples, and then I'll show you some problems to try. Whoopsie, let me make sure I'm in the right spot here. Okay, so I wanted this other thing up. Okay. My bad. All right, so when you look at this graph, I want to see if you can interpret certain things just by looking at it, without even telling you anything much about it. So this graph represents a reaction. And it's really, it looks like 3 graphs, right? Not just one. And it kind of is. But what I wanted to ask you about it was, and of course I keep losing my click here, sorry. Could you tell me from the graph alone which ones are reactants and which ones are products? And what are you looking at to tell me that? So looking at the graph, how do you know what the reactants and the products are?
I would guess that N2O5, I think that is a reactant because it's getting used up and the amount is going down. And then NO2 and O2 are products because their amounts are going up.
Very good. And what I like about your answer is you didn't just look at the equation and say, oh, look, it's in the equation. You did exactly what I wanted you to do, and you looked at the graphical data and you said, oh.
Because I assume this equation is at least somewhat reversible.
It can be, but for our purposes, it doesn't even matter. All that matters right now is that you recognize the fact that as written, when the concentration of something is dropping, it's being used up. And when the concentration is increasing, it's being produced. And so in that context, we would say, this is what's being used up, this is what's being produced, and in the general way to write that would be reactants becoming products. So now the next question is, if we look at the data and look at what they highlighted a specific interval of time on this graph. You can see it right here, right? And they show these little blocks. And you guys all know how to find the basic slope of a graph, don't you? It's rise over run. And if it's linear, it's a constant slope. The difference here is these are curves. But we can still get an average. So if I wanted to measure the average, and again, I'm going to use some symbology here, so I'm going to define it and then write it. The average rate of change of the concentration of, let's say, N2O5, I can express that in the following way. I can say delta for change in the concentration over the time interval, which I'll write as just T. It's really delta T. I'm just going to say T for simplicity. So let's take a look, and let's do that for this one. In this case, let's find the right substance. It looks like it's the blue one. Over the interval that they stated, well, we see the time interval is 100 seconds, right? And we see that the change in the concentration is this change in Y, and luckily it's not scaled well, so they gave us the number. It says negative 0.0019 molar. Why is it negative?
It's getting used up.
Yeah, it's going down. You can see that by the shape of the graph and by how things are changing. If you take, remember, a delta is always a final minus an initial. So it's always the end point minus the start point. So if you end less than you started, you're going to get a negative number. That means if you're using it up, it's decreasing. Now when you divide these numbers, you get something like negative 1.9 times 10 to the minus fifth. And the units here are molarity per second. Notice that as a rate, this makes sense. When you drive down the street, you go so many miles per hour. Okay, because you're covering a distance over a time. Here, it's not a distance, it's an amount of concentration. And so in that sense, it makes sense that it would be the amount per unit time. All right, well, let's look at, in the same time interval, let's look at the other components. Let's define the rate of change of the nitrogen dioxide concentration. Well, so we're comparing apples and apples. We'll see that in the same time interval of 100 seconds, this one increased by about 0.0037 molar. And when you look at that, what you'll find is you get about 3.7 times 10 to the negative fifth. And then I'm going to do the last one, which is the oxygen. So I hope you're just seeing I'm just taking the data right off this graph at that interval and just doing it over and over. And then I'm going to relate them to each other. I'm going to write this one a little bit weird. I'm going to call it 0.9 times 10 to the minus fifth, even though that's the same as 9 to the 10 to the minus 6, just so we can compare the numbers easily. So the 10 to the minus power is the same. Do you notice any relationship among these quantities? Approximately, if you look at the numbers? Like from this one to this one, what's the factor? About.
Around 2.
Yeah, this is about double, isn't it? And what about, let's say, from the same one, just it's easier to do the math, to this one? About.
Half?
Half. Is that a coincidence?
No.
Why? What did I write at the beginning that really shows that this is what should happen?
The coefficient.
Yes. So what I'm trying to show you, no problem. What I'm trying to show you,
Don't we want to avoid using fractional coefficients?
it doesn't really matter. You know, I did that on purpose just so it wouldn't be uncomfortable if you were faced with them. So, but the point I'm trying to show you is that the rates are related by the stoichiometry of the reaction. And that makes perfect sense because until now we didn't really worry about the timing of reactions. We just said, okay, what's the total amounts? And we know that for every 1 mole of this, 2 moles of this are produced. So if this is changing at some rate, this is going to be 2 times that rate, right? And this is going to be half that rate. And that's all we've seen so far. That's all I'm comparing right now. But what it really shows me is that if I work backwards, if I just hadn't given you this equation, we could have used this relationship among the rates to kind of infer the stoichiometry of the reaction. Because the whole thing's all changing at the same time over a time interval.
Wait,
Now,
you're saying that if you
yeah.
looked at the rates, you could find the stoichiometry without knowing the total reaction?
Well, you have to know well, yeah, I guess you could.
Wait, does that mean you could figure out the empirical formula for a hydrocarbon by observing the rate in which carbon dioxide and water were produced relative to each other?
That's a little trickier because that I don't know if that's going to be enough to define it without knowing the original.
I just said empirical formula. I'm not talking about.
No, I know, but let me think about that. I don't want to give a snap answer. I really have to think about that a little more deeply.
Okay.
So
I have to check in with this other thing. I'll
that's
be
okay.
back in like 1 minute.
No problem. So in the end, what I'm really trying to convince you of is just that there's this relationship. Now, the question is there a way to just talk about the rate of the reaction as a whole thing? Because right now we've compartmentalized it. We looked at the rate of this one as its own number, right? We looked at the rate of this one as its own number. And we looked at the rate of this one as its own number. And we see they're all related by the coefficients. I don't know why I just did that. But which one is the rate of the reaction? Is there a rate of the reaction? Well, to do that, we're going to have to take the entire reaction and treat it as one thing, kind of like it has a coefficient of 1. In other words, when the reaction happens once, how fast is that going? Well, there's an interesting way to relate all these to that. So in terms of the overall reaction rate and how it relates to these individual components, it's really simple actually. Since we want this to always be a positive quantity, here's what we would find. That the rate of the reaction in terms of any reactant or product is going to look like this. So let me just write it and then I'll explain. See if this makes sense to you once I'm done. Why are these all going to give the same answer? And why does this kind of work? Like, why am I always going to get one number that's then relatable to all the other parts? Can you see it, like what I did? Highlight this. And then you notice this here. So remember, this is a reactant. And these are products. Let's actually put the numbers in and see if this works. So in here, if I put the opposite of what I had written for this one, I would have gotten a positive 1.9 times 10 to the minus fifth. If I had put this number in and divided it by 2, I would have got 1.9 times 10 to the minus fifth. If I had put this one in and divided it by 1/2, I would have got 1.9. So do you see, no matter which reactant or product I choose, if I define my rate of the reaction this way, I have one number that works. And then I can use stoichiometry to convert it back to any of the individual materials' rate of change. So what am I doing to get this overall reaction rate? If it's a reactant, I'm taking the negative of it. And if for any of the reactants or products, I'm dividing by the coefficient so that it kind of equalizes it down and compares it to one unit of the overall reaction. I know that probably sounds confusing, but I bet if I give you an example, you can figure it out right away. So let's do this example together. So take a look at this and let's see if we can work this out. So I'll start with the given, and I'll define that with for you or with you. So here's the reaction equation in question. It says if N2 disappears at this rate, given, what are we given? Let's see. We're told that the rate of change of N2 is equal to negative, because it's disappearance, 0.20. And it says moles per liter per minute, but that's the same thing as saying molarity per minute. So again, it's concentration over time for the units. If this is true, can you tell me what the rate of disappearance of hydrogen would be? So we know the nitrogen one is 0.2. What does the hydrogen rate of disappearance have to be?
0.6.
Yeah, except if we're talking in terms of rate, you mean negative because it's disappearing, but you're right. Or you could argue, well, you said disappearance, that is negative already. But we know that mathematically we mean exactly what you said. The point, though, the main point that you're making, Ryan, is the fact that the stoichiometry controls it. That it must be triple the rate of the nitrogen being used because it's a 3-to-1 ratio. Well then, what's the rate of ammonia formation?
0.4.
Yeah, and this one, of course, is positive. And now, what's the overall rate of the reaction? Well, it doesn't matter which one we pick. We could solve it from any one of these. All we have to know is it's always positive. So if we pick the reactant, we're going to make it positive. And then if we pick whatever one we pick, we have to divide the coefficient out. So in this case, and I'll just show it for all of them, this would get to 0.2 molar per minute, right? This would be the same thing, but made positive and divided by 3. And this would get the same answer. It's already positive, and we divide it by 2. And if we work backwards, I could have given you the rate of the reaction first and asked you for all the relative rates, and you should be able to go in either direction, because it's really just the stoichiometry of it. Any questions on that so far?
Is this
Oh, sorry. Go ahead.
okay? Sorry. Is this process like, can it be used for temperature and everything like that too, or is it unique to concentration?
So for now, we're going to generally measure and do most of our work in terms of concentration or sometimes maybe pressure,
Okay.
just like we're seeing in equilibrium. Um,
Yeah.
but then we'll work in how the temperature effect gets calculated. There's a whole other equation that determines like how the temperature influences it and such.
Okay.
Um, it seems like always the reactant with a coefficient of 1. Yes, that's exactly right. So in this kind of comparison, the easiest one to work from is the one that gives you a 1, because that's the one that you can immediately not have to worry about anything but the sign being positive. Now, let me show you a couple things I have set up for you to work through, and then let's see if we've learned enough to do so. So this one that says graphical methods is a little worksheet that you can print. It'll probably be easier to print and work through. But let me just show you what it is. It's exactly what we just talked about. Again, you don't have to submit any of these. I just ask you just kind of work on them. And if you want to send them to me for grading, or I could just put up keys or send out keys, whatever's easiest for you. These aren't counting toward your grade. So it's just that you need the feedback. But here I'm saying, okay, look at this data down here, this graph. This time it's on, I tried to make it so you can actually read it if you print it and get, the scaling is easier to do. But you should be able to figure out the equation and the balance. You should be able to figure out the overall average rates at this interval I've picked and the rate of the reaction. But now the one thing I haven't told you is, what if I want an instantaneous rate? What do I do then? Like, what does that even mean? So
Take the derivative.
That's exactly right. But since we're not in calculus, most of us, or haven't had it, we have to cheat. So let me show you what I mean by that. So if we're going to do an instantaneous rate, and some of you may already know this from math, and if you don't, that's okay. You're going to learn more math right now. So an instantaneous rate, instead of being over an interval, this is the rate at a moment in time. And so this is kind of like what your speedometer is telling you when you're driving in your car. It's like, oh, this is how fast you're going right now. On the other hand, if you say, well, it took me 2 hours to go 120 miles, you say, oh, my average was, 60 miles per hour. But that means if you looked at your speedometer, I mean, you were going 60 the whole time. You could have been going faster, slower, faster, and it just averaged out that way. So here's the deal. And again, this is really what calculus does when Ryan says about the derivative. So let's pick, for example, the production of a product. It starts fast, and then it slows down until it becomes constant. Oops. Oh man, what a fail that was. Let me try that again. Right? And so you should know from what you've learned in math that when you pick 2 points on a curve, you're approximating the slope of that curve because you're pretending like it's a line when it's really not. And the farther apart you pick your points, the worse your assumption, right? I mean, look at that. There's no way that's a good approximation of what's going on moment by moment. It gives me a good idea of the overall average if I calculate the slope of that line. But if you think about it, this line or this curve has a really steep slope at the beginning, which means it's a fast rate of change. And by the end, it has 0 slope, which means it's stopped, right? It stopped changing. But in between, that slope is continuously changing its angle. And so what we do, and what calculus ultimately was invented to do, to fix this issue, or to not fix it, but to deal with it, because you can't really fix it, mathematically, is you can take that same curve that we just had, and if I want to know, let's say at this moment in time, the instantaneous rate.
This is calculus.
Yes, but it is and it isn't because we're going to do it the cheap way.
Oh,
Imagine,
come on.
we're going to take a tangent. Oh, I missed. Dang, it's so hard to draw without a ruler on the board. We're going to take what amounts to a tangent line, which means it only hits the curve at one point, the point of interest. And the slope of this tangent line is equal to the instantaneous rate. So what we've really done is we took these intervals and just made them come closer and closer and closer as the limit of that change in time approaches zero, meaning we're zeroing in on an instant. And you're right, the calculus is what was invented to deal with this and do it in a more direct way. But for our purposes, if you do it like this, you'll get essentially the same answer. Now, if you look at the first document I had just up here, when it asks you at this moment, like it says, find the instantaneous rate at 3 minutes, then you're going to have to look at 3 minutes on the graph, pick one of the curves, draw approximately a tangent line, and just find its slope like you'd find the slope of any line. And at that point, you'd be finding how fast the reaction was going at that moment. That's different than the average over a larger time interval, but that's the difference. So that's
But
what
you need to
this,
use the derivative to find the tangent line. If we're just going to approximate the tangent line, why don't we just take 2 points that are close to each other and use the slope of that?
we're effectively doing that because we're just
Well,
eyeballing the
that's a
tangent line and
secant.
everything.
Well, that would be a secant line.
Yeah, but what Ryan's saying is because we're approximating anyway. You're right. This is going to be pretty not accurate, but
By
for the purposes
definition,
of understanding,
by definition, a tangent line is when you have a secant line where the 2 points are the same point.
yeah, I get that. But my point simply is it is an approximation. So in our case, because we don't have the calculus, most of us behind us, we're just going to do it via this approximation. But in the end, the calculus application that we would have used, we're going to give you the results of the already calculus. So those who have calculus or have had it are interested, I can show you how it comes about, and the rest of you don't have to worry about it. Not today, because we're not there yet.
Oh.
But let me just go back to the other kind of problems you need to do. So I've also, again, this is all just linked here. There's some videos. I don't want to take the time unless you guys want to watch them on your own to see some of these effects that I thought were cool. But if you look at the problem set that's linked here, other than this document, it should look very similar to the kind of stuff we just talked about. So let me just show you. I think I just skipped number 8, and the rest I said you should try to look at. But many of these are quick. This is just the definition between initial rate, average rate, and instantaneous rate. Explain how each of these affects the rate of reaction in general using the concepts of collision theory that we just talked about. Here it just asks you to analyze kind of the graph. Again, a comparison of graphs. And then here it talks about the relationships that we looked at in terms of rates of change of reactants and products. I said skip this one because it makes you make a graph, and I just didn't think we needed to take the time because I then give you a couple problems that have the graphical information already ready to go. So the rest of the time, I'm just going to stay here for anyone who wants to stick around and work through the problems now. And then we can do it together. You can work in groups or, ask me as you go, is this right? So that's what the rest of the time will be dedicated to at this point. And then next week, we can spend a little time going over some of the questions that you had. But at this point, the presentation of part 1 is done. So that's our introduction to kinetics. Off you go or stick around and work, but I'm going to stop the recording at this point.